So what is a fully associative cache? It is a single row. There is no concept of an index, right? There is no cache index. So if you have a 32-bit address, then you just have the offset bits, the byte offset bits, and the rest are tag bits. So essentially what this means is you get an address, you split it up into tag and offset, and you place it in the first available column. So if this column is free, you place it here, update the tag. You get another address. There's no index because there's only one row. You place the data here, update the tag, and so on. So once the cache is full, how do you compare? You do a tag match with all the tags in parallel. So if you have 8 tags, you do an 8 tag comparison in parallel. So you would have probably noticed that a lot of hardware complexity is involved in a fully associative cache because you need so many comparators in parallel to be working at the same time. But the other advantage is that there's no concept of an index, so the placement of the blocks is much more simpler and easier and so on. So let us see a summary of the loads and stores. So first thing is you search the cache for an address. If it is a hit, you return the data to the processor. So currently we have just looked at loads. For whatever reason, we have just looked at loads, which means cache reads. We have not yet looked at stores, which is cache writes. We will going to look at it soon. So now we will not look at stores right now. We will do it later. So if it is a miss, what you're going to do is you're going to bring the missing line into the cache from the memory, and you may need to replace a line if the cache is full, and therefore you will use some kind of a replacement policy and then return the data to the processor. So what kind of replacement algorithms? So there is no concept of a replacement in a direct mapped cache. You have to replace the single block that is present in the index. So in a set associative cache, you have the question of which block to evict because there are multiple ways. So one of the policies is random because you can just pick something in random, but it's hardly used. It's not used. So the one that is frequently used is what is called the least recently used policy. So let us say you have 4 ways, and so this is the tag data, and you have data 1, 2, 3, and 4. So let us say the sequence in which it was filled into the cache is this order. Let's say you put the data. Let us call this address, for example. Address 1 came first, address 2, 3, and 4, and then you get address 1 again, which means you are referencing to this. So it is a cache hit. So this was all miss the first time, and you get 1. It's a hit. Now let's say you get 5. Now there's no place here to put 5, so you have to replace one of them. So the least recently used policy means that you pick the one which was not used recently. So 1 was used recently, 4 was used recently, 3 was used recently, but 2 was not used recently. It was used sometime in the past, and therefore you will pick 2 to replace it. So you'll pick 2, replace it, and then place 5 here. So 5 is now a miss, but it is now placed. So similarly, you keep a count of how many times each one and how recently each of this was used. Not a count, but you keep a track of how recently this was used, and based on that, you will replace the one which was not recently used. So that is called LRU policy. It's quite a famous policy. The next one is first in, first out. So whichever came in first, you replace it. That's a simple policy, but not used very frequently. So least recently used is one of the policies that's used in set associative caches. So this is a summary of all the caches. You have a direct mapped cache. You compare the address with only one tag, so the hardware is less. And the data can be present in exactly one index and one block. That is direct mapped cache. This is a set associative cache, n-way set associative. So you compare the address and n tags in parallel, which means the hardware complexity is more. And the data can be present in any of these ways in that particular index. And this is fully associative cache, which means that there is no index and you compare the address and all the tags parallelly. And this is the highest complexity in terms of hardware. And the data can be present in any cache block. So here it is shown as columns, but it's actually just a single row, and there are multiple columns in which the data is placed. So maybe let us stop this lecture here, and then in the next one I'll show an example comparing the cache misses between direct mapped and associative caches.